If vectors always seem confusing, this might finally make it click.
Welcome back, everyone. I am absolutely thrilled to have you here for today's explainer. We're about to embark on a journey, well, actually, let's call it a survival guide journey, through the sometimes tricky but honestly fascinating landscapes of vectors and matrices. If you've ever felt completely lost trying to trace a path around a geometric shape, or, maybe you've been tripped up by the super strict, unbending rules of matrix algebra, yeah, you are in exactly the right place. We're going to use this guide as our ultimate map, breaking down these complex concepts into a really visual, structured blueprint. By the end of this, you're going to know exactly how to draw out your ideas, dodge those common traps, and navigate your way straight to the right answer every single time. So grab a mental pencil and let's get into it. Okay, let's take a super quick look at our roadmap. We're kicking things off with a boss-level puzzle, the vector triangle. Then, we'll master the triangle law, dodge some serious geometry traps, and learn a little trick I call the O turnaround. After that, we'll pivot over to matrix constraints and finally wrap up with some rapid-fire survival tips. 6 steps, 1 solid blueprint. All right, stop number 1, the vector triangle puzzle, or as I prefer to call it, facing the boss level. So picture this, you're sitting in an exam and you're faced with this classic, honestly kind of daunting puzzle right out of the syllabus. It says, in a triangle OLM, R is the midpoint of OL, and T is the midpoint of OM. Vector OR is A, and vector OT is B. What is vector RM, right? Reading that out loud, it just sounds like complete alphabet soup. But here's the thing. Vectors are not just random letters on a page. They are literal, physical directions. To solve a mystery like this, we can't just stare at the text hoping it makes sense. We actually have to sketch it out, label it, and physically trace the route. But before we can take down this boss, we need the right weapon. And that brings us right into Section 2, Mastering the Triangle Law. Consider this your ultimate blueprint. The triangle law for vector addition is honestly beautifully simple once you visualize it. To find the resultant vector between 2 points, like your starting point and your final destination, all you do is sum the vectors along any path that connects those 2 points. It's exactly like giving a friend directions to a coffee shop. If the main road is closed for construction, you just tell them to take a detour down one street, take a left down another, and boom, they still arrive at the exact same coffee shop. In vector geometry, tracing that exact detour is what the triangle law is all about. To make this completely foolproof, I like to break the triangle law down into a strict 3-step checklist. First, step 1, identify your full-side vectors using scalar multiples. Basically, if you only have a piece of a line, figure out what the whole line is first. Step 2, find the reverse vector. If you suddenly need to walk backward down a one-way street, you've got to account for that mathematically. And step 3, just add them together to complete your detour. I can't stress this enough. Physically trace this out. Sketch your triangle, draw big, bold arrows pointing in your direction of travel. Seriously, your own finger is your best navigational tool here. But hey, keep your eyes peeled. Let's move to Section 3, Dodging Vector Geometry Traps, because there are definitely hazards ahead. Now, this first hazard is fascinating, and it's absolutely crucial to understand. I call it direction blindness. This is easily one of the most common mistakes out there. Vectors have a rigid direction. If the vector from point O out to point R is labeled A, you literally cannot just turn around, walk from R back to O, and still call it A. No way. Moving backward against the arrow means you have to flip the sign. You are going negative. So vector RO absolutely must be written as negative A. When you're making your sketches, explicitly draw those reverse arrows and slap a massive negative sign right next to them so you don't trick yourself. Then we run into hazard 2, midpoint mix-ups. Look, a midpoint cuts a line exactly in half, right? Simple. But when you're tracing a detour around a whole shape, you almost always need to travel down the entire side, not just the first half. So, if the problem tells you T is the midpoint of OM and OT is B, remember your scale factor. To travel the full side of OM, you've got to multiply that smaller segment by 2. OM equals 2 times OT. If you forget to scale up those pieces, you're literally going to end up stranded halfway down the road. All right, we know the traps. Section 4, the O turnaround technique. Let's finally go slay that boss puzzle. If you ever catch yourself staring at a complex geometric shape and thinking, I have absolutely no clue how to get from point A to point B, I want you to pull out the O turnaround. The rule is simple. When you're stuck, always trace a path that passes through the origin, usually labeled O. Why? Because these problems almost always define their starting vectors from the origin. The origin is your home base, it's your safe house. By forcing your detour to go back to O and then out to your destination, you practically guarantee you'll be using the exact information they gave you in the question.
And this brilliantly illustrates how everything comes together. Let's solve that puzzle. We need vector Rm. Start at R, end at M. Let's use our O turnaround detour. Our path is R to O plus O to M, so Rm equals Ro plus Om. Let's hit our 3 steps. Step 1, full sides. Well, Om is a full side. We know T is the midpoint with vector B, so scaling up, the full side Om is 2b. Step 2, reverse vector. We need Ro. We know OR is A, so dodging that direction blindness trap, RO must be negative A. Step 3, add them up. We get negative A plus 2b. Rearrange that to look nice, and our final answer is 2b minus A. Boom! Puzzle solved. It's kind of amazing how simple it gets when you sketch it out and follow the blueprint, right?
Okay, we've totally mastered physical paths. Let's shift gears completely. Section 5, navigating matrix constraints. Welcome to a very different landscape. So while vectors are all about sketching and tracing physical space, matrices are about following a super strict, totally unbending rulebook of algebra. And honestly, the biggest shock to the system is this. In regular math, multiplication is commutative. 2 times 3 is 6, and 3 times 2 is 6. Swap them all day long, it doesn't matter. But matrices are stubborn. Matrix math is non-commutative. Matrix A times matrix B does not equal matrix B times matrix A. If you just casually flip the order, you're going to get a wildly different answer. Or worse, the calculation literally becomes impossible. Because of that, the syllabus lays out this rigid framework of rules you just have to memorize. For instance, the maximum size matrix you'll ever face is a 4x4. If you want to add or subtract 2 matrices, the rule is absolute. They have to be the exact same size, or order. You can't add a 2x2 and a 3x1, it just breaks. Now for multiplying, they have to be what's called conformable. That just means the number of columns in the first matrix must perfectly match the number of rows in the second. Think of it like a strict security checkpoint at an airport. If the numbers don't match, you do not pass. And finally, whenever you're doing determinants or inverses, you get to relax a bit because you are strictly limited to 2x2 matrices for those. But hey, even within those safe little 2x2 matrices, there's a massive pothole, the singular matrix trap. The syllabus practically screams about this. You must always calculate your determinant first. Because if you do the math and that determinant turns out to be 0, stop right there. Put the pencil down. The matrix is singular. It's a total dead end. Don't even try to calculate an inverse because a matrix with a 0 determinant literally has 0 inverses to give you. You just write down its singular and happily move on to the next question. All right, we have covered a lot of ground today. Let's bring it all home with Section 6, Final Exam Survival Tips. When it comes down to it, your success is all about trusting your process. Here is your rapid-fire survival list. For vectors, sketch the problem out. Draw your own diagrams, label every single vector, and draw huge, obvious arrows. Then physically trace the path with your finger so you don't fall for direction blindness. And for matrices, verify your determinants first before doing any crazy calculations. And when you do finally calculate an inverse, double-check your adjoint step. Remember, you swap the elements on the main diagonal, but you only flip the signs on the other diagonal. Don't get those mixed up. As we wrap up this explainer, I want to leave you with a little something to chew on. We've just seen that vector geometry is all about sketching highly physical, visual paths, right? While matrices follow these incredibly strict, almost rigid algebraic constraints. But they're taught together in the same syllabus for a reason. How do you think these two totally different mathematical landscapes might intertwine when you move into higher-level math? Is it possible that those rigid matrices are actually the secret to mathematically transforming the very vector paths we just learned how to draw? Something to think about. Thank you so much for joining me today. Until next time, keep sketching, keep tracing, and keep learning.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.